Hey, everybody. Welcome to our next edition of Answer Keys. I'm your host, Phillips. Without further ado, all of these problems involve elastic collisions. And remember that elastic collisions mean that the kinetic energy during the collision is conserved so that the amount of kinetic energy specifically before the collision is equal to the amount of kinetic energy after the collision. And typically this happens when you have like truly bouncy collisions. So don't think of it like two cars that slam together and stick, and there's all this sort of deformation and noise and heat that's created in that process. That's not an elastic collision. But if you have, say, two carts with magnets on them that bounce off of each other without touching, that's a fairly elastic collision in which kinetic energy is conserved. And for all these problems, for any collision ever, in any circumstances, momentum is conserved. So in elastic collisions, both momentum and kinetic energy are conserved, which means that you can combine those two concepts in order to find solutions. So these problems in elastic collisions make what would have been unsolvable problems solvable because now we can write systems of equations for them. So, like with previous WebAssign assignments, I'm going to solve these in terms of variables so that you guys can plug in your own numbers to get numerical values as you see fit, because everybody's going to have different numerical values for these red numbers. So start with givens and what we're looking for this problem. So we have these two blocks sliding on a frictionless wooden track, and I have that underlined because a frictionless track means that energy will be conserved. We have conservative forces in this scenario. Total energy will be conserved. And we are given the mass of block one. So we know M1. It's released from an original height. In this case, it's 5 meters. So we know the initial height of M1. And then we know that there's this magnet to magnet repulsive collision. So we have an elastic collision, elastic. We also are given the mass M2, and we're asked to find the final height that M1 rebounds to after the collision. So M1's going to go down the ramp, bounce off of M2, and then go back up the ramp. And we're looking for how high up the ramp it goes after this collision. So in order to find this, we're going to need to break this down into three little mini problems because there are effectively three parts here, three different events. Part one would be M1 going down ramp. Part two would be the collision. And then part three would be M1 going back up the ramp. And if we want to sort of reverse engineer this problem, I'm trying to find for this last part, I need to know H max. Well, in order to find that H max, how high it goes, I'm going to use energy there. So I'll need to know how much gravitational energy the block has at the end. In order to find that, I'm going to need to know how much kinetic energy it has at the bottom of the ramp. So I'm going to need to know the velocity. I need the final velocity of block M1 after the collision. So going back to the collision then, in order to solve this collision, I'm looking for the final velocity of M1. I'm going to need to know what the initial velocity of M1 was before the collision. And lastly, in order to find the initial velocity of M1, I'm going to need to know the original energy of this block at the highest point. So we're sort of starting at part one, working our way to part three. So for part one, I know that for this block, given that it's conservative forces and frictionless, that the energy initial of block one is going to be equal to the energy final of block one at the bottom of the ramp. At the top, it has gravitational energy, and at the bottom, it has kinetic energy. So that's m1 times g times its original height is equal to 1/2 m1 times its velocity at the bottom of the ramp squared. Solving for the velocity there, I would get v1 is equal to the square root of 2gh0. So that's how fast my block M1 will be moving at the bottom of the ramp. Part 1 done. Moving on to part 2, that final velocity from part 1 becomes the initial velocity of M1 for part 2. And in part 2, we have this perfectly elastic collision. So I know that the total initial momentum is going to be equal to the total final momentum. And I also know that, I'm going to write it on the right side here so I can show both of these equations on the screen at once. I know that the kinetic energy initial is going to be equal to the kinetic energy final as well for the whole system. So what that looks like for momentum before the collision, it's just m1 moving with initial velocity. And after the collision, both blocks are moving. So I have m1 v final 1 and m2 v final 2. For the kinetic energy before the collision, it's just block m1 moving. So its kinetic energy is 1/2 times m1 times the initial velocity of 1 squared. After the collision, both objects are moving. So I have 1/2 m1 v final 1 squared and 1/2 m2 v final 2 squared. So looking at this and keeping this in context, ultimately what I'm looking for in this part of the problem is the final velocity of block 1. I want to know what the final velocity of block 1 is after the collision. I can't just solve one of these equations for that because there are two unknowns in each of these equations. I don't know the final velocity of block 1. I also don't know the final velocity of block 2. So I'm going to solve for the velocity of block 2 in one equation, substitute it back into the second equation, and then solve that for the final velocity of block 1. And that's ultimately what I'm looking for here. Keep in mind that this initial velocity of block 1 is going to be set equal to my answer from part 1, the square root of 2gh0. So moving forward here, I'm going to solve this momentum equation for the final velocity of block 2. So I would have m1 v01 minus m1 v1 equals m2 v2. And v2 is equal to m1 over m2 times v01 minus v1. Going back to my kinetic energy equation now, I'm going to substitute that in for my v2. So my kinetic energy here will be 1/2 m1 v01 squared equals 1/2 m1 v1 squared plus 1/2 m2 times m1 over m2 v01 minus minus v1, all of that squared. So now we're looking to simplify this. 1/2 m1 v01 squared equals 1/2 m1 v1 squared plus 1/2. Now, one of these m2s is going to cancel, and I'll be left with m1 squared on top over m2, and that's going to be multiplied by v01 minus v1 squared, which is going to be v01 squared minus 2 v01 v1 plus v1 squared. Ultimately here, Now I have just one unknown in this equation, right? I have V1, V1, V1. Everything else is known now because I have already solved for the initial velocity of object 1. So in this case, you're going to simplify and solve for that final velocity of v1. And ultimately, this is going to end up being a quadratic. It's going to look a lot less messy when you have numbers plugged into it that you can simplify, right? Like some of these expressions, I can simplify right off the bat. I haven't chosen to do that because I'm leaving things in variable form. But quadratic formula to solve for v1. When you do that, you're going to get two answers, right? Because when you do the quadratic, you're taking the square root of something and that'll have a plus or minus. And so you need to choose the answer that makes sense in the given context. Typically, when you do quadratic formulas, oftentimes you'll get one positive answer, one negative answer. In this case, we would want that negative answer because that would mean it's moving to the left. So contextualize your response here. When you choose one of your two answers for the quadratic formula there, then make sure that you're picking the one that is representative of block M2 moving backwards up the ramp. So it has to be a negative value. Lastly, we would finish up part 3. Now we know the velocity of block M1 immediately following the collision. So now we have its kinetic energy at the bottom of the ramp is going to be equal to its gravitational energy at the top of the ramp. So that's 1/2 M1 V1 squared. That's the velocity at the bottom of the ramp that we just solved for in part 2 is equal to M1 times G times the final height. And that final height will be equal to V1 squared over 2G. And that would be my final answer, substituting in the previous parts. Boom. Okay.